welcome everyone to our 5G webinar today from very sunny Silicon Valley. I'm Judy Little and I am in the Strategic Alliance Group here in Silicon Valley, which is part of the CTO office.
And I'm Ivana Maric. I'm the senior researcher. I work in Ericsson research here in Silicon Valley, and I work on the radio access, really the wireless access and physical layer.
So join us on our journey to 5G, because it is a journey, it's an evolution, and I'm going to sort of briefly go over what 5G is, why we need it, and Ericsson's role in developing it. As I said before, we're both based here in San Jose, so we can work very closely with the ecosystem and with academia. And of course, we work very, very closely with our colleagues in Stockholm, and of course with all our customers around the world. So what is 5G? So 5G is what we call the network of the future. It has many domains, including the radio, edge, the core system, the OSS, the BSS, the actual management of the systems, and services. So it does span a large area. And today we're really going to focus on, I'm going to focus just generally on what 5G is, as I mentioned before, and Ivana is going to take us on a journey with the radio, which is an area that we don't talk a lot about, particularly here in Silicon Valley, and I thought it was of interest to everyone that we go over some of the problems they're trying to solve as we move to 5G. As you may know, we talk about our vision being the network society, and as we move further and further ahead into this, we see huge amounts of data. So what we're going to do is, as we change the slides, you'll see them in our background here. So anyhow, we've now zipped ahead to 2020. And here are some of the key highlights in the figures. And I think what you see is just a huge amount of data on the network. And we see probably 9 times by 2020 what we're seeing today. And a lot of that actually is driven by video. Already we have today 2 billion smartphones, which again is going to enable our network society. And again, our network society is each connection that will benefit from, each item that will benefit from a connection will be connected. So we're talking about billions and billions of connections beyond 2020. We're talking around the $50 billion mark. So as we put these figures together, today Ericsson released their latest mobility report. And I suggest you have a look at that, because these figures are actually even higher. And you can get that on Ericsson's website, ericsson.com, and it gives some amazing insights. And we just see that more and more people are using mobile access. They want it wherever they are. They want it very fast, and they want it very reliable. And they also want sufficient application coverage. So again, we see our industry is just changing very, very rapidly. And particularly we see industries digitizing, and the telecom operators will be going through a transformation in that area as well. We see also the sharing economy, where people don't particularly want to buy things, they can share them, and we see that in new business models like with Spotify and with Netflix. So all these drivers mean that we will move into a new era. And we've got some use cases here, and we're talking about basically lots and lots of different ways to use the network, different requirements, different ways of working, and some of the, obviously the more obvious is mobile broadband everywhere, but we're now looking at sophisticated ways of controlling remote control machines, and this year in Barcelona we did a demonstration there using the cloud to actually operate a machine remotely from Barcelona that was in Sweden. So these technologies are coming out, and of course the other one that we see a lot of is the autonomous self-driving car, where the network will have to be extremely responsive for all the different situations that it will require. And then, of course, we go to the more basic items like water, censoring water and things like that, which again have very, very different requirements. And then what we will see is a completely new applications, new requirements from different industries that we really haven't even thought of today. And that's why it's an evolution, because all the needs and the use cases will continue to change. But what we do know is they will all require something that's very specific for their own use. So here are some of the guiding trends around the network, and we see spectrum as being a critical issue in all of this. It's a very valuable resource, and we will see sharing again, the sharing economy. We'll also see using both licensed and unlicensed spectrum, and again, it's all about efficiency and how do we actually handle this massive requirement with different requirements. And again, the customer experience is going to be a lot more than just speed. It's going to be a lot of other things. And just to point on one other thing here is the security. The security will be key, and we're definitely including that in our research that we're doing right now. So here is what we're working towards, which is one network. Again, we're going to be using logical instead of physical resources to do this. And the idea is that basically the operator will be able to offer services depending on what the actual user requirement is. And what we call this is dynamic and secure network slices. And I think a good example of this is when you're driving in your autonomous car. Well, you won't be driving, it'll be driving on its own. And it gets to a situation where it has to make a lot of very fast decisions. You want absolutely everything to happen instantaneously, as opposed to your toaster with the tray full of crumbs. You can wait a little bit to understand and hear that, but we see this as being a critical part of the network. So there are a wide range of requirements that Ivana's going to speak specifically about as regarding radio, the data rates, and this actually applies to the whole network, but she will specifically talk about radio. The traffic volume density, in fact, it'll be a lot more, as I spoke before, a lot more traffic. Latency, very, very low latencies in some situations, and I've just spoken about the autonomous car. Energy efficiency, we do care about the environment. That's very, very important to us. The different types of devices and where they will actually be. And of course, the reliability. So as you can see, there's a lot of different requirements from the network. Before I transition to Ivana, one of the parts from the mobility report today, which they're saying that by 2021, this is our prediction, that we will see 150 million subscribers on 5G. Okay, so now I'm going to transition to Ivana, and she's going to take you on the journey through the radio.
Okay, thank you, Judy. Okay, so if we want to satisfy this wide range of requirements that Judy just explained, both network elements, the core network and the radio access will have to change, and Judy talked about how we will have to adapt, how we'll do that through network slicing. But I'm going to focus in my part of the talk on the radio access, that is on the actual wireless access to the users. And in some sense, this part of the network is the bottleneck, because you're communicating over a wireless channel, and wireless channel has a limited capacity because of the high channel attenuation, right? The power is lost fast, right, on your wireless link, because of the shadowing, because of the multipath fading, and because of its fundamental characteristic of interference. Right? Now, in any wireless channel, there is interference as soon as there is more users, but this will be more pronounced in the 5G network because, as Judy explained, there will be more users, there will be more data volumes, more higher rates, so that means more signals will be sent over the air, and therefore they will create more interference. So it's very important when we built our radio access network to be clever how we manage the interference. The other problem is that of the mobility. And again, that will be more pronounced in 5G, where we want to support higher mobility, and also we expect to have more mobile users than ever before. Okay, so how do we establish the calls? How do we maintain the calls for these mobile users? Okay. So if we look at how 5G radio access will look, so if we look at the next slide, um, there will be two elements to it. There will still be LTE evolution that is going on in the existing spectrum, meaning up to 6 gigahertz. Okay? And then there will be a new component, the 5G component that we call NX, in the frequencies that are above 6 gigahertz, going all the way to millimeter wave, meaning above 30 gigahertz. But it can also go to the spectrum that are below 6 gigahertz if such spectrum is available. Okay, so it's really a wide range of frequencies. Now, this new element does not have compatibility constraint, meaning it does not have to be compatible with LTE. So we are really, focusing on these requirements that need to be satisfied by all these applications. But it needs to be able to interwork with the LTE network. And I will show you examples of that as a little bit later. Okay? And then eventually LTE will be phased out, and there will be gradual migration of 5G of NX into all the frequencies. Okay? So if we go to the next slide, uh, because we are going to have 5G in such high frequencies, we will have to face the challenges of the high frequencies or attenuation in millimeter wave. Okay? So for one, at the higher frequencies, the signal attenuation is higher, right? So we lose the signal. The range of the signal is smaller. Okay? So for that, we will have to use some MIMO techniques that I will talk about in a little. Then the diffraction capability of the signals is, so the capability to go around the obstacles, it becomes worse. They cannot diffract as well because their wavelengths are very small. Also, they don't penetrate well through the walls. So if you have your base station outdoors, the signal will not really penetrate indoors, which is of course a big problem. They attenuate due to the rain. All those measurements show that as long as the cell is up to 200 meters, that attenuation is not that large, but that means, that gives a limit how big our cells can be, right? So this gives the rise of having the small cells, for example, in millimeter wave. And then we have blockage by obstacles such as humans. These signals in millimeter wave do not travel well through humans, and this is one, aspect that we cannot control or even predict very well. So all these challenges have to be taken into account when we design our network. If the signals don't penetrate well indoors, that means we'll have to have more access points indoors for indoor coverage. We'll have to have smaller cells because of attenuation and so forth. Okay? And then there is also additional limitations because the regulation in terms of transmit power for frequencies above 6 gigahertz are more strict. Okay, so how much power we can actually radiate. And there is also implementation issues that are related to such high frequencies because of the dynamic range and of the efficiency and so forth. Okay, so if we go to the next slide, this slide talks about the spectrum because, as I said, the 5G will span really wide range of frequencies, and we will really have two different designs. So for a lower frequency, say up to 6 gigahertz, we will have more of a cellular design that we have today in LTE, where we have our microcells that are carefully planned that provide a full area coverage. And then complementary for the higher frequencies, millimeter wave, we will have small cells. And those will be used typically in the hotspots to provide extreme capacity and higher data rates that are needed. And now these access points, we expect them to be very dense. We'll have a large number of them, so we want them to be low complexity and low cost. So we're really looking at the two different designs. Okay, so next slide shows an example that really illustrates the benefit of having the system that operates both at the lower frequencies and the high frequencies. So this is an example of interworking that I mentioned earlier. Okay? And this is the simulation that was done here in Ericsson. And what you're looking at in all four figures is a typical Asian city. Okay? So you can see some buildings and the roads. And what these colors represent is the data rates. So the green means the high data rates, so the users are happy, and the red means that really the data rates go down to zero, and so the users don't get any service, and then the yellow is somewhere in between. So if you look at the figure one, the one on the left, this is a case, so we have a network that is operating at 2.6 gigahertz carrier, and it's using a bandwidth of 40 megahertz. Okay? And you see that all users are happy that they get a service, but the service is here 4 gigabytes per user per month. Okay? This is that is the service they get. Now, what we'll need in the, as we go on in 5G, we want to provide higher data volumes. So if we move to the figure 2, the red figure, what happens here is in the same system, in the same bandwidth, the 40 megahertz, we are trying to increase the data that is provided to each user 8 times. So now each user gets 32 gigabytes per user. Okay? And as you can see, the system cannot support this. There is more interference and congestion, and all the users are unhappy. We get very low data rates. Okay? So what we do, and that is done in the figure 3, we now use a system that is in higher frequency at the 15 gigahertz carrier, where we can assign more bandwidth, and in particular here we assign 100 megahertz, so 2.5 times more. And what you can see is that now the service gets better, except for some areas that are still, as you can see, red. So some users still don't get coverage, so we don't have the full coverage. And then in the last figure, figure 4, we are using both systems together. The first one at the 2.6 gigahertz and the one at the 15 gigahertz. And now we can provide required data rates to all the users. We have full coverage, and we have 8 times more data rates. And we were able to provide these data rates at 3.5 times more bandwidth. So we increased our spectral efficiency by jointly using these two systems. Okay? So this is an example how we can benefit from this joint operation and interworking. So next slide shows specific technology areas that we are looking at here in the radio group towards 5G. And I have, so for example, at the left, you can see massive MIMO, massive multi-antenna transmission. That is really important, especially as we go at higher frequencies. And I have one slide for each of these topics. So I will show a little bit more details for most of them. But in general, what we want to have is a flexible and scalable design of our radio access network, both in terms of spectrum. So that means that we want to use, the full pool of frequencies that are available to us, and then, optimize how we assign them to different users and frequencies. We want to be able to support all these various use cases that Judy showed earlier, and to have different deployments like indoors and outdoors. Okay. So let me now go into details of some of these technology areas, and I'll start with MIMO, with multiple antenna. And in particular, very important transmission scheme that will be used, and it's actually already used in LTE, but it will be used more in NX, is beamforming. Right? So we want to send signals from the multiple antenna transmitter such that the signals that are sent from multiple antenna arrays sum up constructively in the direction of the desired user. And that they cancel out into the directions of the other directions. Okay? So what happens is that then what we're doing is we're sending more signal, more energy to the desired user, so he can get better signals, so we can increase the data rates to the user and the capacity, and we are decreasing interference to the others, right? So in that way we are also increasing capacity. Okay? And because we are, and that is shown in the figure 1, and then because we are sending, because we are focusing our energy, we can actually extend the range to which our signals can transmit, so we're extending coverage, and that is illustrated in figure 2. And that can be used for both high and low frequencies, both for NX and LTE, but it's really important, and actually it's crucial for operating in millimeter wave bands because of this attenuation that I mentioned. Right? So this is how we will really provide the range in high frequencies. Okay? So because of that, what we have in 5G is beam-centric 5G design. Okay, so what it means is that we want to organize our data transmission such that everything that is necessary, that is control and data, is sent on one beam to the user. So once the beam is established, it's almost like being connected to the network. Okay, to connect it to one base station. Okay, so it gets all the necessary information on one beam, and then as it moves, due to the mobility, it will be transferred to another beam and so forth. And this is what we call beam mobility. So the next slide shows the multi-site connectivity, which is another area that is very important. And what it means that it enables a user in network to be connected to two base stations at the same time. Okay, so the figure 1 shows the case of the intralayer, which it is connected to the two base stations of the same layer, for example, 2 micros or 2 picos. Okay? And that is beneficial for two reasons. First, these two base stations now act like distributed multiple antennas, so we can achieve higher data rates to that user. And it also gives robustness to mobility, because as the user moves, it might lose a connection to one base station, but it will still be connected to the other one and gives diversity. Okay? And then the figure 2 shows the example interlayer where the user is connected to micros base station and also to the pico base station. And so this is an example of this interworking that I mentioned before, because you can have one of these base stations being the LTE, working the LTE system, and the other one can be NX. And that is good because it can happen that a user loses connection to the small cell, to the pico cell, and it will still be connected to the microcell. Okay, so this is how we want to design our network to allow for this multi-site connectivity. Okay. The next slide shows the machine type communications, which is really a range of applications, and some of them, again, you saw earlier, Judy explained. This is going to really to IoT, to Internet of Things. And because of the requirements of the machine type communications, we are looking at this really as a technology area, and that's why I'm explaining it here. And in particular, we are looking at the two types of machine type communications. We have massive MTC, and these are characterized by large number of devices that we want them to be low cost. We want them to have a battery life that is long, and therefore they should use low energy. They should have low energy consumption. So you can think of the sensor networks, for example. And to satisfy these requirements, we want to design our network such that we have efficient sleep modes. We want these nodes to wake up only periodically or if they're triggered by events that they're observing. And we want to have a flexible device bandwidth because we're not sure which bandwidth will be available for them to operate in. And then they should be able to do what is called device-to-device relaying, meaning that the device does not have necessarily to talk to the base station because maybe it's not able to if there is no full coverage, in which case it will talk to another device because we have large number of devices, and then that other device will relay information to the base station. And that provides for coverage extension. We see actually examples of that already in LTE today. Now, the other type of machine type communications are critical MTC, and here are the one example that is the self-driving car that we heard earlier. The other example is control of the windmills and even remote surgery. And you can imagine that for this type of application, we really need ultra high reliabilities, like to 10 to the minus 9 at least, and a very low latency. And this is end-to-end latency is about 1 millisecond. So how do we design a network that can provide such really demanding requirements? So what we're looking at, for example, is very short transmission time interval. That means that we cannot really use techniques like interleaving, which is typically used because of the fading versus fading in the channel, which means that we take the signals that are going to be transmitted over different blocks, and then we interchange them, we interleave them, and send over the channel. These techniques cannot be used because they increase latency. Also, if you look how we do coding, or how we design frame structure, it has to be designed such that we can provide on-the-fly decoding, meaning as soon as you start receiving your bits at the receiver, you can start decoding them. So that means you have to send all the pilots or reference signals at the beginning of the frame. Right? So going to the next slide, this is a very important technology area that we're looking at, which we call ultra-lean design, and what we mean is the energy efficiency. Right? So this is really important for 5G. We want to be kind to the environment, and here it's more of a challenge because we will have more infrastructure, we will have more users. So we really have to be aware how that we are not using energy when we don't need to. So what we want to do is we want to minimize network transmissions that are not related to actual data delivery. Okay? So if you look what is done today in LTE, and that is shown in figure 1 in this slide today, is that so this little green boxes represent data that is sent from the base station to the user. And you can see this gray underlying line, which indicates the reference signals and the broadcast system information that is constantly sent. Okay, so even if there is no data to be sent, the base station will broadcast this information, in case the user wants to start transmitting. So in the 5G, we want the ultra-lean design, and now you can see in the figure 2 that these gray signals are gone. They're only sent when the data is sent. So there is no always on reference signals, and there is no broadcast system information. Now, how do you do that? That brings a big challenge because you have users coming in that want to connect to the new base station, or they have to know to which base station they are connected. So really, it really poses the challenge to the designers how to make this ultra-lean possible. But what this provides is the energy efficiency, right? Because we are using less energy transmitted from the base station. And it also actually decreases interference in the network because the reference signals in one cell are interference to the other cell. Okay, so next slide shows the decoupling of the system and data functionality. So what we'll have in 5G, we'll have two separate planes, one for data and one for system control. And here is an example in figure 1 where we have a micro base station sending necessary system control information to its users. And then we have a user that actually receives data from a picocell that is in its vicinity. Okay? So these two are completely decoupled. Or, as figure 2 shows, you can have user that is connected to the same base station. So from the same base station, it's receiving data and the control, but there is again separation. So the system control is sent, in this case, it's broadcasted to all three users, and then there is specific data that is sent to each other. So because they are decoupled, as the data rates and the capacity increases, as it will in 5G, the system overhead will not, follow this increase. So that is really important. And the final one is that of the backhaul. Right? So by backhaul, we mean how do we provide all the data from the core network to the access points. And if you look what is done today in LTE, each base station has a point-to-point high-capacity line-of-sight link, okay, over which it receives all the data. And that uses dedicated technology and dedicated spectrum. So it's completely decoupled from the access. But tomorrow we are going to have a large number of these access points. We will have small cells. And we will not have the line of sight to each of those access points. So this kind of technology will not be possible. So it's a big issue actually that we are looking at here, is to how to provide backhaul for possibly thousands of access points, many of them indoors and outdoors. And actually, what we are working on, for example, is the multi-hop, wireless multi-hop backhaul as a complementary solution. Okay, or we'll have some fiber grid and so forth. So the approach that will be taken in 5G is the integration of access and backhaul, which means that now both access networks, so from the base station to the users and from the network to the base station, will use the same spectrum and it will use the same technology. That means we can now jointly optimize our resources, right? If one of them needs less spectrum, we can give it to the other one and so forth. We will also have simplified hardware because now with one radio we can, we can serve both the access and the backhaul. Okay, so this is also an important aspect. So if we go to the next slide, this shows the 5G testbed that was made by Ericsson to evaluate these 5G technologies. It contains some of the elements that I've talked about. It has massive MIMO, it does ultra-lean transmission, and it achieves today about 10 gigabits per second. It uses OFDM, as we expect will be used in the 5G. And as you can see here from the picture, it is currently in one big box. So you can imagine that there is some challenge to bring it into a small handheld device that users will actually carry. And building such a test bed is actually very useful for us to see, what are the challenges as we implement some of these technologies that I've talked about. Okay. So in the summary, what we see is 5G, we'll see that we'll have one network, one common network platform that can support all this wide range of applications that have very different requirements. And what is really important is the performance. Now, the performance meaning in terms of the rates, in terms of the latency, right, as we talked about, and in terms of the reliability, and this will differ for different applications. And this is really important because we expect this technology, to be here for a long time, in 2030s and so forth. Okay? And so there are some applications that we don't yet envision that might bring us more requirements. We want to really be flexible and able to provide for them. Okay? And as you see in the 5G wireless access is a very complex problem. Because there is only that much capacity on the wireless channel, and we have to be able to support these higher rates. And we expect peak rates that will go 10 times or even 100 times more what we have today in LTE. So
okay,
that's about it.
So as you see, Ivana has sort of explained what goes on in the 5G radio, and as she mentioned, 5G wireless access has got a lot of different requirements. So we've got in a few questions, and we can start going through them. One of them is, do you think 5G will be an evolution or a revolution? It'll be an evolution, and we see some of the technologies already out there right now. We see network function virtualization and software-defined networking, which will take us in that direction. So it will be an evolution, and we will see many iterations of this as we go along. What are some of the key technologies for 5G? Well, I think Ivana has talked a lot about the 5G radio and how important that is. But of course, as I mentioned before, there are many domains in this, and they will all be part of 5G, and they will all happen at different times. And we talked about the core, the edge core. We talked about the management and control, OSS, BSS, and of course the services will be all an important part of this. Again, this whole initiation is being driven by different users' needs and different requirements. And as I showed before, the data is really, the data adoption is really taking off, and it's a business-driven and it's a society-driven requirement. So we will be meeting the needs of these particular situations.
This one, is it too early? So there was another one. Is it too early for these technologies to exist due to the fact that 4G is still in the early stages of adoption? I think that one thing why is it too early is, we don't have yet a standard for 5G. The first standardization meeting just happened maybe a month ago. And in order to to build this network, we need standards so that we know how to build it. And this is actually standardization process. It's gonna come out in phases. There will be phase 1 and then phase 2, and it just started, and more meetings will come next year. So in that sense, for sure, it's too early. We also are not sure about the spectrum assignments and so forth.
And that's again on the wireless access. So
Yeah.
other things are happening in parallel. So it's I think this is what makes it really exciting. It will be a journey, and it will all come together. And also too, as I mentioned in the use cases, there are use cases that we haven't thought about. And while robotic surgery seems absolutely amazing, and we see more and more virtual reality, I think we're going to see other requirements that we will be able to use to do different things that we haven't even thought of. So that's actually what makes it, I think, extremely exciting. And okay, so going on to the next question, what are the requirements need to be met for 5G development? And again, I think we talked about this a few times, but one of the key things is it's got to be fast, so the data rates have to be quick. It has to be able to deal with traffic volume density. It has to be very responsive, and we're talking about latency here, and we go back to the self-driving car when it gets into a situation where it has to make split-second decisions. Energy efficiency, we need to, corporate sustainability is very, very important to Ericsson. And again, the reliability, and the reliability is key. And Ericsson's in a very good position because we do the end-to-end network. And so we have a very good view of what's happening. We work with a lot of partners. We look at lots of different new technologies, and that's what will keep us in the lead. I mean, we will continue to be innovative. We've led all the other generations of wireless, and we will lead the 5G wireless. I'm just going through the questions now.
So okay, I don't know how will impact networks.
No, just this one here.
This one?
Yep.
So the question is Ericsson working with IEEE Standards Association related to 5G? So absolutely, we will, there is all this, the standardization will go to 3GPP, and we will actively participate in that and in the standardization process. So, and as I said, the first meeting was held a month ago, and we'll have more meetings coming up. Yeah.
Do you want to take this one here?
This next one is
5G development.
What are the So the question is, what are the uncertainties and challenges of 5G development? So I think, some of the challenges, at least on the radio, side, I talked about. Providing what is expected is 10 or 200 times more data rates. We want to have peak data rates that are up to 20 gigabits per second, or on the average, we want to provide 1 gigabit per second, which is something we don't have today. So can we build a network that does that? We want to provide for a mobility that is up to 500 kilometers per hour. So, challenges like that are really hard to meet. And then also the problem is big challenge that we're seeing now is that of latency, of having 1 millisecond end-to-end latency that gives, over the air even less. So how to design networks like that. So this is all these requirements in terms of wireless access are difficult. And then again, you can think of, because of this wide range of requirement, the different approach would be to, design a specialized network for each of these applications, right? And then you optimize it. What we are doing is something really different. We want a common network, right, that can now be adapted for each of them. That's why we need network slicing and things like that. So I think all these are challenges to build such a network.
Okay, so one of the questions I've got here is, when is the actual rollout for 5G? And as I mentioned before, this is a journey, this is an evolution. A lot of the domains are in research, and we will see changes, and things will be quite different. But as I mentioned before, in our mobility report, we're saying that by 2021, we'll have 150 million folks using 5G. So we will see some happen sooner than that in different areas, perhaps for a different event or special event. But the radio is planned for 2020 because it has to go through. Perhaps you can explain the 3GPP.
Yeah, so there is because of the 3GPP process, because it has to go through all the we have all the meetings. So first they make a working group, and then they discuss, and then go through all the steps of the standardization, and then it has to meet some requirements that are posed for the system before it can be rolled out.
So this is for the wireless access,
yeah,
the 5G wireless access.
I mean, one more thing about this challenges, going back to the question. Yesterday I went to, there was a 5G summit here in Silicon Valley, where they were showing the demonstrations, where they started to do demos with self-driven cars. And one of the challenges is that they all go nicely in the line, and they move, they're just controlled by the network. If a sudden event happens, that needs really fast reaction, which means the latency has to be really small. What happens is this event where they start to oscillate, so the cars start moving back and forth because of the delay in the network. The network cannot support this. And today we still don't have a mechanism to resolve such a high latencies. And this is also issue they had probably with gaming, or the virtual reality. Where this is another example that you need very low latency and so forth.
So I think Ivana makes a very important point, that this is a very collaborative process as we're moving along, and we're all by collaborating we can actually solve these problems in a much better way, in a much faster way. And throughout the network, throughout the whole process, we will be engaging with academia and other industries and the ecosystem in this journey.
Exactly. You can see really companies talking to each other, and that's why we have these 5G events to kind of design on to decide on the unified way how to build this network. Okay, because this is all still in the process of designing, and still many of it is still in the research.
Last question.
So. Yeah, so the question is, what are users really lacking with 4G, and how might 5G fill those needs and wants? So we've seen examples of that earlier, right? Some of these applications cannot be supported by 4G. So if we are going towards the Internet of Things, right? Or I talked about the machine type communication, right? If we have massive machine type communication, some of them, you want to monitor infrastructure, to have some sensors, some of these can be supported. But having these critical machine type communications, examples that we just explained, that cannot be supported by 4G. And we really didn't see even, there's been a lot of talk about small cells, right? But we don't see that many of them deployed. Most of them are the femtocells in the, in the homes, but we don't really see that many small cells covering hotspots. Okay? And this is because of the challenges, because we didn't really figure out how to use them and how to architect such a network. One example I mentioned is the backhaul. If you have thousands of these small cells, how will you provide backhaul for them? Where will you put intelligence and things like that? So this is another thing that we are looking if we can provide for these small cells in 5G. This is another challenge we're looking at.
Great. Another question we have is, if you want to learn more about 5G, where would you suggest you check for info? And I mean, again, there is a lot on our webpage, www.ericsson.com, and it's continually being updated with the latest announcements and trials. We're doing trials all over the world in different areas. We did one in Korea a couple of weeks ago, which was publicized. So if you want to sort of see what's happening and how it's going, that's where I suggest you do. And, as I said, the use cases that we haven't thought of, some of the ones that we're starting to look at now are mines, different things we never thought we could be able to do, which is going to increase the safety in these particular areas. But again, the use cases go on, and as Ivana said, we need a very different network to be able to cope with such diverse needs from the users.
And actually, this is the IEEE Society that organized this 5G summit that I mentioned that was held here yesterday in Silicon Valley. And all the talks, everything is online. You can listen to them. You can probably find the link if you just Google 5G Summit Silicon Valley. So you can see what companies are thinking. And again, there is a lot of collaboration with academia here.
And again, I go back to the fact this is a journey, and it's continually changing, and which makes it very, very exciting. And there is a lot of resources that you can find through our webpage. And being the leaders in this technology, I think this is probably the best reference. Do you want to talk about?
So the question is, tell us more about yourself. How did you get into your field of work? My background is in really wireless. I did my PhD in wireless, and I was a postdoc at Stanford working on wireless. And really, the problems where you have many users that are simultaneously communicating. I worked on network information theory for my research during my postdoc years here at Stanford, and then. And when I joined Ericsson, which was about 2.5 years ago, I started working on 5G. It was actually surprisingly well fit, because really what my training was really now applicable, because this is what you have in 5G. I mean, I started that in my first slide. You'll have many users that are interfering with each other. So how do you combat that interference, or even better, how can you exploit that interference and treat it as a useful signal? That's really of importance. And so I can apply some of the work that I did during my PhD and after that in these problems in 5G. And now we're working on problems of channel coding. That's another big problem for 5G that hasn't been decided. We're talking to other companies. So what kind of coding you use to add redundancy to your data before you send it in the wireless channel. Today, LTE uses turbo codes, but there are other types of codes that we are looking at. So that's again another thing that I was familiar with. So that's how I started working on the radio for 5G.
Okay, so my journey is a little different. It started in New Zealand, where I'm from originally, and actually started in a research lab for what we would call today a small startup. I don't think they just called them private companies in those days, and that was a very interesting area, and then was acquired by a larger company, and I actually got into the manufacturing, which is a very different route. Having graduated as a technologist, manufacturing was quite a challenge, and a lot of different technologies were being introduced into manufacturing at the time. So it's a lot of change and a lot of challenges with things being automated, particularly with machinery. So that was pretty exciting. Then I went to Sweden for a while working with Ericsson, and then back to New Zealand. And then I came to the US here in '99 and worked with some of the large tier 1 operators. And that was a very exciting time, because in '99 we were just launching a GSM, so the start of the GSM systems here. And also worked on other technologies at the same time as well. And then finally came to Silicon Valley in 2009 to work with a lot of the ecosystem and the partners here, where we felt it was really important to have close relationships, so we could find the best way forward, and also to really understand what the network had to be able to perform to meet some of these requirements.
Okay, one more question. In terms of quality of service, how can we control or assure quality of service in 5G, especially on the transition? So I think that's a good question. What we'll have is this, what we call ITU requirements. So ITU is International Telecommunication Union. It's actually part of UN for telecommunications that poses what are the requirements. And you can find, again, if you go on our website, you can see what are the requirements for 5G and how actually they changed from LTE and from 4G, and then so they pose these requirements that need to be really satisfied when we build our the actual system. So they are like the UN of telecommunications. So they will. You have to, when you design your system, you have to make sure that these requirements that are posed by ITU are satisfied.
Okay, well, I think we've finished the questions and really have enjoyed talking to you all today about our network of the future, which is very, very exciting, and it's great to be here in Silicon Valley and be part of all the changes that are here. And of course, it's great to be with Ericsson, who are the leaders in this area. So again, thank you so much for your time and listening to us, and I do hope you find time to go to our website and see all the exciting things we're doing there. Perhaps, Ivana.
Yeah, thank you very much for finding time to listen to this. And again, yes, in radio, we have a big group working on the radio access in Ericsson, like 500 people. And the reason is because it is a difficult problem, as I said, and we are looking at many techniques, some of them that until now just existed in academia, and that we are now bringing into as a practical solutions. So I think it's a very interesting time working at in wireless and in general 5G.
Yep. And a special thank you to we for making this possible. Very much appreciate the opportunity to talk to you all.
Yeah.
And the IEEE Woman in Engineering as well. Thank you very much.
Thank you.